Absolutely sorry for the inconvenience. I hope I'm audible now. All right. So we have with us Dr. Shubhasri Roy, sir. He has ME and PhD degree in computer science and engineering from Jadavpur University. Sir has academic excellence, which is reflected as he has prestigious gold medal and the university medal he received from Jadavpur University in 2006 for his ME degree. He has been an assistant professor with the Department of Computer Science and Engineering at the University of Calcutta since 2010. His research interests include cloud computing, wireless sensor network, and high performance computing. Dr. Khatwa has an impressive professional background as well. He was an R&D engineer with Tejas Networks India Limited, where he received the Best Employee Award in 2007. Simultaneously, he is also serving as a lecturer in Jadavpur University. He has been honored with several prestigious awards throughout his career, including Vishwasvarya Young Faculty Fellowship from the Digital India Corporation, Government of India for the period from 2018 to 2023. His accolade also includes the Young Scientist International Travel Award from the Department of Science and Technology, Government of India in 2013. Dr. Khatwa is going to speak today on resource management in environment. We are honored to have you, sir, today. I would now like to welcome Sir for the talk. Thank you.
Thank you, and very good afternoon to everybody. So I see some offline and online also. So if you have any question during my presentation, so please unmute and ask me. I will make it interactive if possible. So so it my screen visible to and audible to online participants. So please any one of you can unmute and tell me. So, well, anyway, so those who are in the offline, so mostly from computer science background or some other stream as well, all from computer science. Well, so today I will discuss about large-scale resource management techniques in cloud. So by this large-scale resource management, I mean already we have used some form of resource management techniques in the operating system. So I call this kind of resource management in the waste level as the small scale. But whenever I'm talking about the cloud, any computer in the world, if it is connected to the net, so it can be a resource of that environment. So think about the environment of the resources where every computer that is connected to the net can be a resource. So it can be considered a billions of nodes are the resource to you, and you have to manage those resources. So that's why I make it a large scale resource management techniques. So anyway, those who are in the offline also there. So how many of you are teaching operating system or cloud or distributed? Is there anyone? Yes, good cloud distributed. So all these things are there. So we have also experts in the offline also. So well, so we will find some similarity of the resource management at the waste level, and we will see that how they can be extended in the large scale cloud environment and why we cannot use those techniques in the cloud also. So before that, let me discuss about the cloud platform a little bit, and then we will discuss about the resource management and what is the issues and how it can be resolved at that level. So we already know that in a distributed computing environment, we have a number of local area networks that are connected by each other through some switched one to form a large wide area network. And we have a function that needs to be that needs to be computed using the resources in the wide area network. So think about a function. The function is computationally intensive. The function is data intensive. By computationally intensive, I mean, if we run this in a single computer, it will take a huge amount of time that you cannot solve within a day itself. By data intensive, what I mean, that it try to perform some data, the data itself you cannot store in a single computer. Think about the social mining. The social graph, I have to mine it. So if I want to store the social graph, it itself has millions of nodes in the graph, and how can we store it in a single computer? So if it is a computational intensive, if it is a data intensive, we cannot store it in a computer. So we need to decompose the function. So first thing, that this such kind of large function, decompose it into sub-functions and distribute across different nodes that are connected by the net. Some form of network connectivity is there. And our objective is to provide overlay or abstractions on top of that. As if this network connected network looks like a single computer. And after decomposing the function, they becomes a process. And all these processes are running in a single computer in an abstracted mode. So even though they are running in a large distance, one node can be running in US, the other can be running in India, but once it is abstracted, it looks like they are running in a single computer, this black box, and all these processes like a simple functions and one function calling others in the same computer. So if we have a very large function, so we can decompose and distribute across various nodes and run it. So this kind of environment can be well visualized by this kind of distributed ways. So how can we abstract this? So this can be abstracted by formation of a distributed operating system. So on top of the kernel of different nodes, we can establish the ways functionality at the distribution level. Once we have an abstraction with the distributed ways, we can write our applications that will assume that I am writing my application observing a single computer, because this distributed operating system gives us a view of a single computer. So write your application, put your function call to the ways, and the distributed ways will resolve all the complexity of managing large number of resources. Now, can you tell me, any one of you, what may be the issue if I go for this kind of model? What may be the challenge I have to face? Anyone? Why this fail? Obviously, it is failed. You know that there is no such distributed operating systems that solve everything. If it's solved, then cloud computing will not come. This is one challenge. It should be homogeneous, so that in a cluster environment, in the co-located environment, it has to be solved. The other is a scalability. As the scale of the cluster increase, because we have to solve the deadlock handling at that level. So look at the resource graph, resource allocation graph of a single nodes. So if we add one extra node, look about the global weight for graph. So how can we solve this global weight for graph at that level if we increase millions of nodes? So think global weight for graph where we have millions of nodes involved. So it's not scalable. We cannot use it. So what we do, we simply change this slightly to make the operating systems at the local level. We call it a network ways. So the network ways are simple ways, but that can be accessed remotely. It allows the services to access its resources from a remote location. And using that NOS services, we can have a small middleware layer that will solve the resource allocation at the global level. So the local resource allocation will be still handled by the NOS, and the global level, it will be handled by the middleware services. So by using that hierarchy, we can solve the heterogeneity and the scalability issue by this architecture. Now, this kind of architecture can be used for any kind of environment. If I'm talking about data handling, large-scale data analysis, so this middleware can be Hadoop or big data analytics kind of things. If I am using a large scale of IoT devices, the middleware can be IoT platform. If I am talking about the virtual resources, this middleware we can call it a cloud computing platform. But the structure is same. Even if it is a big data analytics, the platform, the middleware is a big data platform. If it is a cloud resources, it is a cloud computing platform. If it is a IoT management resource bank, this middleware now called the IoT analytics platform. But this scale wells, it supports heterogeneity, it supports scalability. So this kind of platform we refer to as a cloud computing platform. So we can write a cloud application that will give the resource request to the cloud platform, The cloud platform hide everything and it will use the various AWS services to access the local resources at the node level or the things level. Now, another change, big change in the cloud environment is that, does it allow this kind of distributed connectivity using switch one? No. What they does, they put all the resources in a common place, in one building itself. We call it a data centers. The resources are not like one thing is in US, other thing is there, and there is a cloud platform. That's not the thing. So all the resources they put in a large building and form this kind of things. You can observe that this one you can think. I don't know. So if you look at this one is one rack in a data center. So you can think that this is one rack in the data center, and in each rack you can see these are the blade servers, each of servers. So this rack you can consider like a one local area network, and on top of each of the rack there is a rack mounted switch that connect the multiple racks and forming a very large wide area network kind of things. But we can say it's a metropolitan area kind of things because the scalability is like a wide area network but placed in a single building itself. So this is the cluster of nodes you can consider that will be managed by the cloud platform. And in cloud environment, such a data centers is called availability zone because this is your availability. So if we have some competition, we can use that zone, we can use that data centers to put your computational task or data storage task. Now, the nearby data centers are basically connected by some high-speed lead line connections. They call it a region. So to have a practical idea, in our India also, Amazon has lots of such regions. So in our Mumbai, we call it a Asia Pacific Mumbai region. And this Asia Pacific Mumbai, we have the code of AP South 1 for Amazon. And this Mumbai, co-located places, they have three different regions. The regions are AP South 1A, AP South 1B, AP South 1C. So each of these ABC are the data centers. And in ABC, they have such a large amount of resources they have available. And these regions are basically connect to the rest of the regions through public network, the normal internet. So this is the overall structure in the cloud platform. We have lots of regions. In each of the regions, we have some availability zones of the data centers. And each data center, we have lots of racks. Each rack can be considered as a local area network having lots of blade servers. And in that blade server, you can place some computational task or your data intensive task. So if we consider the resource management point of view, now we can observe that how we can schedule the resources and what are our challenge. And before going to that, let me discuss about the server itself. If we consider each of the blade server, there is another requirement for cloud that they need a special software called hypervisor. On top of each of the servers, they have this hypervisor or virtual machine monitor. This one is installed on top of each. So this one is your hypervisor. That was not there in other servers, but even in the cloud, in the data centers, they have a blade server. On top of the blade server, they install this. What is the task of this hypervisor? It basically allows the creation of the virtual machine. It can create any number of virtual machine considering the virtual resources requested by a particular user so that the task can be run inside the VM. These virtual machines will use the resources of the physical machine and use it. So if we consider the resource scheduling, we need to consider first level of resource scheduling at the operating system level that already we have studied in our graduation course. The next level of resource scheduling will be at the hypervisor level that will schedule these virtual resources. Basically, that will map these virtual resources to that physical resources. Next level scheduling has to be done for a particular data center. That how can we place the virtual machine into the host? We call this problem as the VM placement problem. That for that data center, we have lots of virtual machine requests come. How can we place the virtual machine? In which host the virtual machine should be executed? So this problem is called the VM placement problem. And then the next level, we have to consider this task. How can we map the task to a particular virtual machine? Should we run this task in this VM or should we run this task to another VM? So this is called task placement problem. So if I look it in a bottom top down, we have at the top level an application user have some task placement problem. We have to place the tasks to the task can be a computational task or it can be a data intensive task. It has to be placed to some VM. In the next level is the VM placement problem. Those VMs has to be placed into some of the hosts of the data center. Now, the next level, once the set of VM comes to the hypervisor has to schedule it to the physical resources. Once the request comes to the physical resources, we will use the OS scheduling algorithms. We have lots of process scheduling, IO scheduling, memory scheduling. So this has to be done by the host operating system. So let me start one by one. So first I will start discussing about the scheduling at the hypervisor. Then I will discuss about the scheduling at the data center level. Then we will discuss about the scheduling of the tasks at the application level. So first let me discuss about the scheduling problem at the hypervisor level. So till now, any question, any issue here? So what are the three levels of resource scheduling we are going to discuss now? Is that clear to everyone? Right. So the first level, obviously, we have a hypervisor. So what is the problem? The problem is that you can see that we have one blade server. This is one blade server of a data center. Obviously, it has a hypervisor to launch some virtual machine. For example, in that case, we have 3 virtual machines running. Each of the virtual machine has their guest operating system, their own library functions, and a set of applications running there. Now, if we see how operating system schedule the resources, so this is the structure. You also teach that operating system, you know that there is mainly 2 modes, supervisory mode and the user mode. Actually, there are 4 modes, but in our graduation level, we teach only user mode and the supervisory mode. But actually in that x86 architecture, we see that there are 4 modes. They are called the rings. Ring 0, ring 1, ring 2, and ring 3. The ring 0 is the supervisory mode. They have the high privilege, highly sensitive instruction. That is, if we run 2 ring 0 instruction, there may be a race condition. The resource may have affected. And as we go higher, the sensitivity reduced. And at the top level, at the ring 3, the instructions can be shared. So they will not affect the final resource usage. So you can see that the application and the library, they map to the user level and the operating system map to the privilege mode. So that's why whenever the operating system executes some instruction, there is no issue because the OS is running in the privilege mode. But if a user, for example, if the application or if the library try to execute this instruction directly on the hardware, sensitive instruction, they will be trapped. So we already studied that the OS trap this and the operating system schedule the resources. Now, the main challenge of the resource scheduling at the hypervisor level is who will resolve the race among the guest OS. Because there are 3 guest OS, so these 3 guest OS may run their sensitive ring 0 instruction directly on the hardware, and the OS are running in the privilege mode, so they will parallelly execute it, and there is a race condition. So the main challenge we have to solve here is how this race will be solved. Any idea that it can be used to solve this problem? The problem is clear to everyone. As long as we have a single computer, we have a single OS, so OS resolve and execute it. But in that environment, there are 3 virtual machines running. Each of them has one operating system. So this OS, whenever the OS trying to access the hardware parallelly, since the OS is running in the privilege mode, the hardware does not complain it, it executes, and those are sensitive instructions. So that is the main challenge. We have to transfer the control to the hypervisor, but how we can control? The challenge is how it can be controlled, because this guest OS does not know anything about that. So there is a system call comes to that operating system, and the operating system directly execute. Who will give it to the hypervisor? Because we have not changed anything. That is the main challenge. Solution is I have to transfer the control to the hypervisor. But the thing is how we can do that. So this can be done by using that ring. What it does, whenever we install an OS in the virtual machine, they place the guest operating system in ring 1 instead of ring 0. That means the operating system of the virtual machine are not running in the privilege mode. They are running one level up the privilege mode. So ring 0 is the privilege mode and ring 1 is one level up. So clearly, whenever the guest OS try to directly execute on the hardware, it sees that the ring 0 instruction coming from ring 1 at the lower level privilege. So the hardware will not execute and send the trap to ring 0. Now in the ring 0, hypervisor is running. So hypervisor will trap all the requests coming from the guest OS. So whatever you say, that we have to somehow redirect to the hypervisor. In that way, it is redirected. So this solution is called the full virtualization technique in cloud. But it has another problem. The problem is that context switch requires some instruction which are very sensitive whenever we are performing the context switching. The Intel architecture, what they does, they don't send a trap, but stop executing that instruction. So that means if someone tries to perform context switch other than the base, the hardware does not send any trap and also does not perform that. So in that solution, the DS2S failed to perform context switch. So obviously, even though we see a very simple solution, it fails. So what they did, they virtualization. Question or inquiry? That is the issue with online and hybrid mode. Well, so what they does in para-virtualization, they put guest OS and the hypervisor both in ring 0. And what they does, they modify the kernel. How they modify the kernel? For each system call, that is replaced by a hypercall. So system call means we are calling an operating system. So we are calling a hypervisor. That's why it is called a hypercall. So they modify. So that's why this is called para-virtualization. And the issue with the window, because window operating system is proprietary, they don't allow you to see their kernels. And we know that the Microsoft has a problem with the cloud environment. So what they do, they modify their kernel itself and they make a window version for the cloud. So for Windows, they have separate distribution. So whatever the window operating system we use in the desktop is not the same we use in the cloud environment. So they modify itself, provide a different distribution, and then the modified kernel, they have a hypervisor call is there. And for other operating system, whenever we are installing in the guest OS, at the time of installation, they modify the kernel because they are not proprietary. So during that, they can modify the kernel, and the kernel replaced, every system call is replaced by a hypercall. And also for calling the hypercall, performance does not degrade higher. Can you tell me why? Hypercall is no. Yeah. I'm talking about bare metal, not the hosted. So in that case, this hypercall also does not incur lots of overhead because it does not require context switch, because both is in the ring 0. It's a normal function call. If there is a context switch, this is overhead. But for example, system call, whenever there is a system call from the user mode to supervisory mode, it's overhead. But for hypercall, the overhead just calling one function. It does not perform context switch because both are in the ring 0. So basically, I discussed about the full virtualization, para-virtualization. The virtualization itself is a lot of topics. What Seth told, that we are talking only on the bare metal, not the hosted or the other types of things, because it itself required another lecture. But at least we have understand the resource scheduling problem or the issues at the hypervisor level to deal with. And I discuss only the CPU resource. If we see another resource, for example, suppose the network resource, how it can be resolved. So look at that. This physical server has only one LAN card. So that is assigned to one IP address. Now each of the virtual machine has to be assigned another LAN card, virtual LAN card, and another IP address. And how can this be done? So this is done by a software bridge. So for example, in case of Gen, they have a Gen bridge that create a virtual switch, connect the physical switch of that host, and for each of the virtual machines, they create a virtual interface and create a software switch. So whenever you send a packet using the software switch, it redirects to that particular IP address of that host. So that way the network resource can be scheduled. Another is the memory resource. The memory resource already we have a virtual memory, so mostly done. So only one level they put extra level that is called the machine level. So for each of the virtual machine, you can see that they have a physical memory and a virtual memory like the traditional one. But here the virtual machines are running on top of a physical machine. So one level up is the memory machine block is also there. So we need one extra mapping between the physical memory of the virtual machine to the machine memory. So this is done by the hypervisor. Now, can you tell me one thing? That suppose we have 1.5 GB of RAM, and each of the virtual machine required 1 GB of RAM. Can we run this? Dynamical allocation, but how cloud solve this problem? So this is solved by content based page sharing. Dynamic means I have to share some page, and dynamically I have to minimum memory, obviously. So this is done at the level. So this one in the cloud environment called content based page sharing technology. What did that? Initially the VMs does not share, they have their own machine memory block, and periodically hypervisors scan it to find the similarity in the blocks. How they find the similarity? By using their hash value. So they perform the hashing of each of the blocks. If the hash value matched, that means the content is same. So once they find some similar content, they delete one of the content and just change that pointer. So not necessarily that exclusively the memory will be used. So what I want to say that in that memory resource scheduling, the hypervisor efficiently schedule the memory block so that the total may be much less available in that physical system also. We should not be thinking that I have one memory, 1 GB of memory for each of the virtual machine, so the total sum should be greater than this. That may not be the case here. So these are some of the techniques that you use at the hypervisor level to schedule their CPU resources, their network resources, or the memory resources. Now let me go to the one level up, that at the data center level. So once we reach the data center level, the user sends some request for the VMs. We have a set of VMs requested. We have a set of hosts available in the data center. So we need to place the VM into the physical machine. So that's why this problem is called a VM placement problem. So let us see how we can solve this problem. So let us model each of the RAID server like a big rectangle. So each of the width of the rectangle like a normalized value of the CPU. The width of the height of the rectangle is normalized value of the RAM. So given a set of physical machines in a data center, we can easily represent this by a set of big rectangles. And each of the virtual machine requests, they can also be considered by a small rectangles, because the virtual machine has a small CPU, small RAM. So what is our problem? We have to place this small rectangle inside this big rectangle, right? So can you tell me what is the problem in algorithm you studied? What problem it's match? For the students also, we have lots of big rectangle and you are giving some small rectangle. The small rectangle has to efficiently pack inside those large rectangles using the minimum number of rectangles. What is this problem in operating system called? Fragmentation is an issue. If there is a fragmentation, then we need large. But if we can place efficiently, fragmentation is not there. So what is that algorithm? How can we pack this allocation problem? But what algorithm it is called? Suppose we have a bag, we have some items. The items has to be efficiently knapsack problem. But the knapsack problem has only one bag. We have more bags. So knapsack problem has an extended version. What it is called? Bin packing problem. So this is called a bin packing problem. You can consider these are the bins, right? We have lots of bins. For example, there are 2 bins and these are the items. The items has to be packed inside the bins and efficiently. We have to use the minimum number of bins to pack it. So this is called a 2-dimension 01 bin packing problem. If we consider the network bandwidth, if we consider the IO, so dimensionality increased. So it can be considered as a multi-dimension 01 bin packing problem. Why I call 01? Because either the virtual machine is placed or it is not placed. We cannot say half of the VM is placed, it's not. So it is a multi-dimension 01 bin packing problem. We have to solve it. Now, how can we solve the bin packing problem? So we have to take a decision. The decision will be very simple. So xik, for example, the ith item has to be packed in kth bin. So xik will be 1 if the ith item is placed in kth bin. Or we can say if the ith virtual machine is placed in kth physical machine, that decision becomes 1. Otherwise it is 0. So we have to find those value of the variable that optimize this. Now from that decision variable, we can find another variable called the UK. What is UK? UK is also a binary variable.
that UK will be 1 if it is utilized, if that bin is utilized. That means if the kth bin is assigned at least one virtual machine, it is used. Otherwise, it is not. So we from that xik decision variable, we can easily derive UK. Now what is our objective? Objective has to minimize the sum of the UP into the cost of that using that bin, because they are heterogeneous. So using each of the separate bin has separate cost. Now U into C means U means it is used and C means the cost of that. So we have to take a sum of this and that has to be minimized. And the cost can be weighted average of the two dimensions in the CPU and the RAM. And what are the constraints? The first two constraints is that the resource should not exceed. Resource should not, the sum of the resources of the virtual machines should not exceed the available physical resource. The third constraint says that a VM has to be placed exactly in one of the hosts. It cannot be in more than one host. And the last one, UK must be greater than equal to XIK. That guarantee that if XIK is 1 for a particular K, the UK must be 1. Otherwise, it is 0. So this is the problem we have to solve it. Now, for a small cluster, this solution is okay because we have lots of variables. So this is not practical for a large data center like Amazon or Google. So what we do, we basically use some heuristics to solve this problem instead of solving this optimally. Heuristics can provide a near optimal solution. And in the operating system, we have seen the good heuristics are best fit, first fit, and the worst fit. That can be used. And in our lab, we have used some best fit algorithm to solve this problem visually. We have solved this optimal for a small data centers. We have also solved for a large data centers using the best fit algorithm. Now, what is the fitness? Can any idea that how can I define that this virtual machine is best fit to this physical machine? If we consider this algorithm, if we consider this like a rectangle kind of case, we have small rectangle, large rectangle. When we can say that this rectangle is best fit to another rectangle, how can we say? By looking at the shape. Yeah. Okay. Yeah. Yeah.
Basically, all are available.
Mm-hmm. Mm-hmm.
And you are able to see the resources currently being used.
Mm-hmm.
Like all the things.
Mm-hmm.
Character, the base suited physical machine you can write from the screen itself.
Mm-hmm.
And put drag and drop.
Now the question is.
And another aspect.
Mm-hmm. Mm-hmm.
That is also manual.
Mm-hmm.
Another aspect is the like this.
Mm-hmm.
That's automatic.
Mm-hmm.
And automatic means suppose in a cluster environment you have got 30 machines. And in any point in time, one or two machines goes down. Goes down in the same, it's like some CPU takes somewhere, something other takes. One CPU takes, other CPU takes over. But there are many permutations and combinations. Out of that, sometimes one machine takes. Then within a second, the DM goes, multiple DMs are running in that physical machine. All where gets distributed and goes to their own machine. Like, so something is happening, some magic has happened, now somebody is going. And all these are visible to the data center engineer who is just managing.
Yes.
And this we have experienced quite some time. Many number of occasions. I was coming in the office in the morning and the data center engineer called me up and said, sir, this has happened and there is no problem, no interaction, nothing. All the applications are running. All are available from Microsoft. I have experience of hypervisor or Hyper-V for a long time. Thereafter, the company has shifted. VMware also, some other also, because it's all government company is basically done for engineering. Any kind of you can know.
Okay.
Because the kind of machines on the ways, you may have Linux or you may have Windows or various versions, various editions. And only thing you have to say that your hypervisor, what is the highest version you can support. All happen. And it's all heterogeneous environment. And in a, like the person who is developing hypervisor software, for him there is a lot of action, for him lot of thinking, lot of algorithms.
Yes, yes.
Many more things. And that you cannot imagine the kind of ways we are now teaching much more complex than
So just
all the things of ways as well as many others.
so just to say that you say that one node is down and immediately it is running somewhere. Now in the live migration, in the live migration, what they does, they just copy the process state to the others, and in the post copy approach, as there's a page fault, it copied from there. Now if it is down itself, how it can perform that live migrations? How it can go?
Data is not all your ways. Machine itself is the storage.
Suppose there is something.
See, that is the beauty of the cloud is the storage system has to be robust enough. That is your machine.
I just told you that there are two things. Two things. One is there are two things. One is the data that is in the network storage service.
Data means in the cloud where all related files stock in the form of a ESD file. That's a data in the storage. Everything in the storage.
So there are two approach: pre-copy and post-copy in the live migration. So no.
I am talking of the scenario we have been gone through.
Now there are two things. One is availability, other is fault tolerance. Can you tell me how this fault tolerance occurs in live migration? Storage two parts: in memory and the backend storage. I am talking about the in memory part. Then I am talking about the in memory. So obviously that will not be in the VM. Obviously. So
that's connected to another 20 racks of server. That is basically fine.
Now tell me that if a physical machine down, what happened to the in memory part? There is lots of page. I'm talking about the page in the west page. No, line migration we should not lose it.
What is the importance is the consistency of data. What is the data? It is database management system. Database management system is taken care by the database itself. So there the hypervisor role does not come into picture.
Obviously.
So I have my Oracle database. The Oracle will take care of everything. We have got clustering taking database itself. Also there is a there are many techniques available for data.
No, just my one thing is that how can we perform the live migration in memory? No, I'm talking about the cloud storage. I have a VM runnings. I have to perform the live migration. If this failed, so there are two approaches we use. One is pre-copy and the post-copy. So latest we are using the post-copy approach, right? But the fault tolerance separately deals with that. But we cannot say that if it's suddenly down a host, all are immediately magically moved to that. It cannot be. That's my main point. Yeah. Okay.
Sometimes it was down, no? When that Rounak came to the Mukesh ceremony that time. So that's a very rare occasion.
So now my question is that we are having the data centers, we have lots of requests of the virtual machine, we have to place it. So for that, this is the best fit algorithm we have used. So I'm talking about the fitness. So whatever you told, that which one say pitch good. So we can find some aspect ratio. So based on that aspect ratio, we can define the aspect ratio of the physical machine, the aspect ratio of the virtual machine, which match that is the fitness. Multiple queue can also be there for different types of VMs, but I'm talking about the single type of
different size of this. Now, one way of defining the fitness can be that how it fit to that, so that the wastage or the fragmentation will be less. So that can be defined by the aspect ratio in case of rectangle kind of case, and where it fits. But this one does not reach so close to the optimal one. So what we do, we map it to the genetic algorithm. We use the genetic algorithm here. So this initial solution can be mapped like a gene. Then using the crossover and mutation, we can prune it. By using some epochs, we can find some better solution. And we have observed in our lab, where we run it in a VMware kind of environment, we have 6 basically servers, and then we simulate to large number of server itself. Now, if you observe that for this 20, this is the lower bound that find from the optimal solution, and the next one, so check this. So this one is basically the lower bound that found from that optimal solution, and this is the genetic algorithm that provide. Now you can see for this one, it's very close to each other. So using that aspect ratio and pruning using genetic algorithm, it reached very close to that optimal solution kind of things. So with that, we basically assume that the total number of virtual machine, total number of physical machine needed to pack is reduced. But for a data center, what is their objective? The total running cost has to be minimized. And this running cost based on their power they consume. So for that, our fitness should be defined based on the estimated power. So not only the minimum number of physical machine to be used. So what they have done in the literature, not only us, the others also, they are working that instead of minimizing the total number of physical machine, I have to find the fitness based on the estimated power. That if we place that virtual machine to that host, and if we give some information about the task running in that VM, I have to estimate what is the power consumed. Because if I can reduce the total power consumption, the total cost, electricity cost will be reduced. So that can reduce the carbon dioxide footprint as well as the electricity bill. And that can reduce the total cost of the data centers. So the fitness should be defined in terms of the estimated power for placing the VM to the host instead of reducing the total number of physical machine. So the question is, how can we estimate the power? What we have done in our lab, we have defined some power model. What we do, we have some blade servers. So these are basically the VMware-based blade server we have in our lab. We put some benchmark workloads. We have some power meter. The power meters is easily available. You can buy from the Amazon also. That can give you the what is the power consumed by that servers. So what we run those workloads, measure the powers, and collect the data. That for that workload, what is the CPU usage, what is the RAM usage, what is the cache miss, and all the parameters we measured. And for that data, what is the power measured there? So we collect lots of data, pre-process it, and build some model, either using the linear or non-linear. So basically, we consider some mathematical modeling of the linear, some mathematical model of the non-linear case, and also we use some form of machine learning to model this, because we have to estimate that for this kind of task, what may be the power required. So for that, initially we have used this kind of linear model. So where the model you can see it's a line kind of things. That PU equal to Pmax minus Pmin into utilization plus Pmin itself. Now we have to find the value of the Pmin and Pmax. So can you tell me how can we find these two values? Anyone? How it can be determined? That we have some data collected, the different powers for different utilization. Now we model this like this, PU equal to this. So there are two unknowns. What is Pmax? What is Pmin? Because these are linear line. So Pmax minus Pmin is the slope and Pmin is the y-intercept. And we have to determine this. And then we have to estimate for a particular utilization what may be the power. So how can we determine that Pmax and Pmin from that equation? Anything? See, when u equal to 0, what is PU? The Pmin. That means just turn on the server, don't put any workload and measure the power. So that is your Pmin of that host. Similarly, if u equal to 1, then you can see it's Pmax. So put lots of workload so that the utilization shows 100%, and then you can measure Pmax. Once we get Pmax and Pmin, using that linear model, we can easily find what is the power consumed for a particular load without running this. If we say that this virtual machine at a load, not this. It gives you revenues. Okay. So using that, we can use this as a model, estimation model, that we will give that this virtual machine require this kind of load, then what can be the estimated power? Again, this is not the actual, because when it runs, it may utilize and maybe something different. But if we have this kind of average utilization of the CPU, then we can estimate what is the power. And based on that estimated power, we can provide the fitness. So this has some simplification of this we can use, or we can go for some nonlinear, where instead of u, we can have alpha times u to the power beta. And using the set of data, we have to fit it to get the value of the alpha beta along with Pmin and Pmax. And most of the literature, they don't use either of the case, they use a piecewise linear kind of things. So for different two pieces, for P1 and P2, they measure two power for two utilization, and we can consider that for that piece it is somehow linear, and we can use it. And based on that, we can integrate those powers to get the energy consumption. But this continuous function can be again converted to the discrete form and take the summation to get the estimated power for that. And using that estimated power, we can find the fitness of a virtual machine to a host. And also we can use some regression model as well. So for single variable, we can use that alpha plus beta into CPU, where alpha is Pmin. But for that multivariable, so we can consider not only CPU or memory, it can be CPU, memory, IO, or others. So we have to find the beta cap to optimize the sum of the square errors. So this one we can use, or we can use a lasso regression that will solve the problem of the overfitting with that. So using the second term to be used here. So any question here, or we can also use the mathematical model as well, that is machine learning model as well, to estimate the power. So any question? In that discussion. So any question here? Because we have only 5 minutes, so the third model I think you cannot use. That is the waste level that we have worked. That the task mapping basically. This task mapping also similar way we have solved this. So I think this one we cannot have enough time to discuss this. There is some mathematical calculation, and basically this works we have published in IEEE transaction on cloud computing, and the last one also, the extended version of this, we have also published in IEEE transaction on services computing. So if you want, you can go through those transaction papers. So where they are well accepted to whatever in our lab we have proposed. So basically our lab does not have enough resource. We have only one rack having 6 VMware nodes, and we have some simple power meters. So using that, we have whatever we get, and mostly we have simulated using the cloud sim. So, and we have seen that it also will accepted in the transaction paper as well. Yeah, we have a separate NAS. So where the storage is in the NAS, we have a NAS separate in the blade server. But whatever I am talking about, the in-memory part. The in-memory needs some time. So that's a different part, the fault tolerance and the availability. I'm not talking this part here. Whatever you are talking about this, that how easily they manage this fault tolerance and the availability. They consider. So here we mainly consider at the top level. The user gives some task. Yes. Exactly. Yeah. And in fact, our team, we are working at the user's level. First, user gives some task. We have to find in which VM we have to place. This is the first level of research. Yeah. There are lots of basically the broker architectures. Yeah. You have to put that. So actually, this whatever we publish in the services computing, transfer services computing, there we have used the game theory. So automatically map these tasks to the VMs using a multi-cloud environment, because there can be different providers. So in which provider, which data center we have to place it. Mm-hmm. Mm-hmm. Exactly. Mm-hmm. Mm-hmm. Everything automated. Yeah. Mm-hmm. Exactly. Mm-hmm.
I used to call them that in stadium like
Sure.
like a stadium.
Mm-hmm.
I have seen once in Bangalore that EMC's data center.
Yeah.
That is for the whole world. They are managing the data
Mm-hmm.
center from India.
Exactly.
That data center is in Bangalore.
Yeah. So actually,
got only two data centers, one in India and that is not in some other country.
yes. So I visited this Zurich supercomputer center in the Europe also. So I have seen that they don't have the AC also. So their processors are liquid cooler. So I personally visit there and see it, that from there the processors are cooled by that special liquids. Yeah. Yeah.
In the data center
Downstairs.